Hi everyone, Cześć from Poland. That will be continuation on the previous stream. So part 3 is continuation on part 2. There will be a bit about accelerometer and in addition how to configure Bosch magnetometer BMM150. And again, we will start from the website. So Bosch Sensor Tech. And actually, the company is evolving, and if you go, of course, we will go to magnetometers, but if you will check what equipment it provides, and you go further, there is smart glasses light drive. So I wanted just to show that there are some works on that to be provided, probably distributed to develop applications. So this is very interesting that the smart glasses might be under development by the community. I've checked that in community that website have some issues, but you can inspect the page, what applications can be done with that, and actually there is nice video, some screenshots. So I would say it is something like HUD, head-up display. So something that was in the fighters, probably is in modern cars, but currently it can be on as part of the equipment, everyday equipment, actually used for messages, navigation, and for AI for sure. So that's nice things. It actually provide the light sensing to show information on the screen. That's amazing, and it can be used with some MEMS. And yeah, actually, if we go to what is topic of current stream, to magnetometers. So there is new version for augmented reality, virtual reality, and actually the BMM150, which is widely available, it costs about $7 or similar. The size is 1.5 millimeter on 1.5 millimeter, so it can be in the glasses for sure, and yeah, it can be used for outdoor, indoor navigation and head movement tracking. So for navigation, yeah, the orientation and the direction should be there. It uses also I2C, I2C, and SPI, and I will show actually how to configure to use I2C, but based on that you can configure to use SPI, which will be faster probably, as yeah, the new part, and that might be looking like there is some wasp. So I was using, because it is plastic, so I was using hot glue, glue pen, and it holds additional wires that connects the signals, so ground and positive, to do selection. And as you know, for the previous video, the BMI, to select the interfaces, so it used, let me check again, so SC is connected to plus, and SAO or SBO or something like that. SAO, there is SAO on the board, but in documentation there is something different. We can check. There is ground, so that's actually the physical interface to configure and to use with and actually to boot on the address that you need to provide in program, and also on the other side there is SCX and SDX. You can find, you will not see, but on the bottom there is SCX, SDX, and SCX is slave clock and SDX is slave data. So this is additional E2C to the slave, so to the magnetometer, and it used similarly 3.3 volt and the same ground to level the potential. So it's like to have the same level of the signal also, to decode 0 and 1 properly. So same level should be there. So just additional from the IMU is to use SCX and SDX to the SCL and SDA. Let me check of my other. So I'm checking with that more complex for some other maybe bigger drone, but the pinout is similar. So there is SDI for data, SCX for clock, and SDI for data. So you need to connect one with the other, and additionally what is in the magnetometer, so to use the configuration that I selected, and it's on the GitHub. So additionally, so VCC should be to 3.3, GND to GND, and then we have SCK and SDI for clock and data, and there is SDO, CS, and PS. So SDO should be connected to the SDO should be connected to negative. CS, so chip select, also to negative to use I2C, and then PS, which is protocol select, should be connected to plus, and that's protocol select is I2C. So let's check the documentation also. And the measurement is micro Tesla, so it's magnetic strength, and there are some ranges. 1300 for XY axis, and you see that 2500 micro Tesla to Z axis. So actually, yeah, the data sheet, it's there. So it's very similar to BMI160, but the configuration is different, and actually you see that the magnetometer can be used for heading information, tilt compensation. So tilt you can know from gaming machines what is tilt, and yeah, for compass of map rotation, navigation, augmented reality, and so gaming and smart glasses as well. Okay, let's go let's go briefly through that. So that's electrical operation conditions. Okay, accuracy 2.5 degree plus minus. Okay, and also the ODR, I was mentioning ODR, so it's output data range, so data rate, so it's in hertz. That will be important. Okay, ODR, output data rate. Okay, you see that for low power, which I was using, it allow more than 300 Hertz. But okay, there is sampling, and it's not so accurate. It's maybe faster. I haven't checked that yet, but yeah, there's a lot of things to check. So with lower ODR, you can have more samples to take the more accurate values. But actually, we will be trying to do same, having less accurate, but we will try to remove the noise, and let's the calculate for the drone purpose. Maybe you can check with lower ODR as well. But yeah, I think that series, it's third part of this series, but it will have a lot of material, so maybe there will be some rewards after. It's gathering knowledge actually, and having the intuition to work faster, because yeah, the orientation, that is the current topic itself, is very complex topic. So it's there is a kinematics, so it's about the timing, the orientation, the position, the velocity, and yeah, so the acceleration as well, in physical terms, but without the forces that cause those the motion actually. So kinematics about the motion without the forces, and then we will working with, yeah. So this is the frame I will be using for that project. Not expensive. So actually the motors gives the dynamics and the forces actually. So when we go from the kinematics to the dynamics, so from motion to how to cause that motion, we need to go through the estimation actually to calculate the relation between the forces and the motion, and the control to control that the motion and the forces, and yeah, that will be with the loop from transmitter. So it won't be on the AI. We will start with the operator, with the transmitter. So we will be sending the signal for okay. So for pitch, it's like tilt. But it's pitch. For roll and for yaw. So again, so pitch is around that axis. Roll is around actually, okay, the horizontal axis here is horizontal axis is roll. The vertical axis is yaw, and the third axis is pitch. So depends how you configure your sensor. So actually, in that case, x is to the so that, okay, x is to the west, y is front, so right is x, front is y, and z is horizontal direction. Okay, so that's, and I will show again that that's in Polish it is płytka prototypowa, and in English it will be prototyping board, and that one fits perfectly between the screws there. It fits perfectly there and sits, so that will be the place, and it's already checked. So with some addition with the hot glue, that can be placed there. There is Power distribution board PDB for 6 serial LiPo, so from 3 to 6. It allows that battery to be connected. So 4 6S, but I was checking that the motors have great thrust with 6 serial LiPo, so 22, 24 volts and 14 volts, which is 4 serial. It gives less thrust, but both can be checked actually. All right, let's go back to the documentation. So how to configure? So I was mentioning the preset. Okay, recommended presets for repetition and output data rates. So you see that for more than 300 and documentation code in GitHub, and the one I was working on using 400 preset for low power preset, and repetition for X, Y, and Z is three times. So you see that there is high accuracy preset. It used 20 Hertz, and it gets sampling of 47 for X, Y, and 83 for Z. That's why, yeah. So Z, it's the yaw actually. So rotation around the Z axis. It will be more accurate, and that is mainly used to point to the north, and the unit is micro Tesla. Okay. Okay, let's scroll. Not now. So register map. Okay, but we have one thing. So we have documentation, and again we have the driver. So this is also on the GitHub. Okay, sorry for chaotic presentation, but this is what it is. So you need to take BMM150 CH and defines, and there is example as well. So you can check examples. It has data render interrupt, but it's not about the kinematics and the control and the other stuff. So let's leave it for later. Okay, so I think we have covered that. So I will close that. Where it was, it is very similar. Okay, so you see SDO is I2C address selection. Chip select used to set one. Okay, CSB, and yeah, we are almost there. It won't be long. Okay, and you see that what is the address and how to configure a CS, chip select, and SDO. So I think we are using ground, so that address will be used. And digital interface, it was digital. The pinout, okay, and that one. Okay, so PS, so protocol select. To use I2C, there is plus, so voltage, and it is different configuration for SPI actually. So you have to check if you want to use SPI, AHRS, so attitude and heading reference system. So currently I'm checking different equations, let's say, and relation, proportions, and yeah, I'm also building intuition with with the equipment. So you know that there is this flight AHRS function that gets information from IMU, and for accelerometer, gyro, and magnet data, but we'll focus on the BMI currently, as that one needs to wait. There is a mess and wrong equations, because also to use just one prototyping board, I needed to reverse the BMI to have one axis align. Always other will won't be aligned, or it should be on the bottom of that prototype board. So I will just show a couple things from how to use acceleration and gyro to show pitch roll and orientation. And okay, so this is that part. And what is important there, so if you have raw information, you need to use the scale factor, and the scale factor, it is from documentation for the configuration 16G. If you use 16G, so the scale factor is 2048 receiving bits per G, and actually this is the scaling that should be used for 2G. Is that value, and this is from documentation. Similar is for gyro. So for configuration with gyro 1000 degree per second, it's 32.8. For 2000 degree per second is 16.4. And similarly, field range for XY, as you saw in microteslas. So there is degree per second and there is microtesla. And I think the field resolution is 0.3. But it's not used. I'm using acceleration and gyro currently. And to show why it's important, because that says documentation, and it appears to work. And what else? You see that the BMI160 acceleration configuration ODR. Oops, sorry. Oddzwonię później. No. Sorry. So there is 1060 Hertz and 16G. Okay, the range is important there. You can show the bandwidth as well, the power mode, and for gyro it's same ODR and 1000 degree per second range. Okay, and I think. Okay, and auxiliary, which is magnetometer, is for 400 Hertz, and the preset is low power, which are 3 repetitions for X, Y, and Z from documentation. Okay, the rest is in my GitHub actually. So configuration for Nucleo G431 KB. Okay, and if we are talking, if you are talking about the documentation, so I'm keeping there as well, and it's good to have also the pinout for STM. So I will tell how to read that, because it's problematic as well with having knowing the orientation. So if you look having the USB on top, and I've marked with black marker the ground pin. So second from the right is ground. So based on that, you know what are the pins, because A, D, and so on, or sorry, values, let's say, PA4, PA3, So this is what you find. Let me open. So this is what you find configuring the peripherals. So those pins. So ground is having the USB on up, and second on the right is ground. So this is the reference, and you see that there are those pins. So you need to do mapping between that picture from ST website, or from internet you can find as well easily. If you type Nucleo G431KB, pinout or connector pinout, that will be in the documentation as well. And what I was not showing previously is I2C, and you see that I'm using fast mode, so it's 1000 kilohertz. Okay, so it's 1 megahertz. It's 1 million per second. Okay, I thought it's hertz, but it's kilohertz. So it's 1 megahertz. Okay, and there is nothing more. I'm not using DMA. I was thinking to use, but and not now. And maximum output speed, I set it very high. So if you go to the configuration, you can just select between low, medium, higher, very high. So very high is there. No changes. No, thank you. Okay. Don't save. Okay, so the pinout, you know how to read that as well, with knowing the orientation for the Nucleo board. What are the parameters that gives the values, and how to read those values, actually, to know how to read those values, how to interpret the values, and how to scale. And if we go, I also needed to tell what is the X, Y, and Z. So actually the physical orientation is different, and to have like some general notation, I just change the axis. So x-axis is Y and y-axis is X for that, and actually different configuration will be for magnetometer, but that will be later if I will see that it works. So we can go to the control and estimation, and actually build the wall, connect the microcontroller with IMU, with electronic speed controller, motors, and radio. It is prepared, but the algorithm needs to be finished. Okay, just to not take too much time, I will just run, and I will just go for the first part. So H-tan, so arcus tangens, so from tangent, from Y and Z we take the roll. As mentioned, we need to know the angle of our orientation, and roll is around X, and that's roll, and pitch around X. So roll around Y, pitch around X, and there is the magnitude of Y and Z shortly. And yaw is just calculated as integration of gyro through time also. So timing is important, and the timing is from the timer, which has 1 megahertz resolution. So 1 million of the second, so one million, microsecond US, millimicro. No, okay. So 1 million, one over a million over million is a microsecond. Okay, so we take that from the timer and we start. Actually, what we start, we take the tick from the beginning, and then actually we take the difference in microseconds. We pass to AHRS state. Okay, we have the difference, and the simple version is to integrate the gyro. So gyro is angular velocity. So how what is the rate actually of that through instantaneous time? So we integrate yaw actually, and yaw have this problem. I can show if I comment that part. If you rotate still around one axis, it adds the angles. So actually you don't need to know how many degrees it rotates, you know just the orientation. So actually you need to trim. It's not really normalized, but to trim yaw to show just 0 to 360, not 400, 500, 600, and how many, and you can have a plus one side and minus second other side actually. So that's how it works. And actually what is important, the magnitude, and if we normalize the acceleration, we will have the ratio, but the magnitude, that show how good is the sensor also, because it has value of 1. So magnitude of 3 axis is 1 for accelerometer. I'm doing here some calculation that we will omit because some are correct. Maybe we'll show something, or some are correct, some are wrong. And that part is also more complex, as it added the this is more about the tilt also from the magnetometer. So we do correction for yaw, so rotation around the z-axis, but I need to check multiple time again. Okay, there are some angular velocity and should be acceleration and some other values as well, different trials. And if we go there and if we start, okay, so we see we have the data from magnetometer, acceleration again. And you see that scale for acceleration, and you should see for gyro, but it's more crazy. But live expressions, so you can add just typing the name you are using, and we have why is there, because we have that global variable AHRS, so we can actually remove and we can add it again, and you see the real changes. So just first trial, so roll is around y-axis, and you see that from 180 degree we went through about 90 degree minus. This is the 0, and we go to plus. If we put that side, it's 90. For the pitch, we have up, we have 90, and it goes some strange. You see some strange value. It's not 180. There is minus, there is plus, down, and yo actually, so we have, maybe we start that way. So if we go 90, we have 90, and this is for gyro integration just. So if we go that way, we have 180. Okay, it keeps, so it's prone to drift, so it should change and so on, but it keeps actually. So we can use it already. There is 270, and we have 360, which will go. We will cut it with that part. Okay. But also I'm checking other versions. So let's see. We have pitch 90, but then we have 180. Another version of calculation. So for where are angles? We have angles there. So different version of equations, and we have 180 for roll and pitch. There is 90, about 90, and there is minus, so we'll flip that. So we have roll, but yeah, that's strange as well. So so roll actually is 0, but it shows good pitch, and yeah, it's the roll actually, because the roll is also roll, that is, so this is okay. So this is the roll, and it's to the moon is pitch, it's pitching. Rolling is like the barrel, that's rolling. But the yaw there, it's around the z-axis, more about. So the yaw, it's incorrect, so you see there are some issues. And yeah, maybe there is some drift for the values. And what else? There is that version of calculation, so we have 90 as well. So actually same, but yeah, it's limited. It doesn't go further, but actually drawn in first version, we need to be stable in that position and go just up and down. So accelerate, so it should have negative acceleration and positive acceleration in that way. So negative if it fights the gravity, and positive, or maybe the other way. I need to check again what is positive acceleration, what is negative acceleration. But mainly minus 9.8 is the gravity value. Newtons per meter square per second. Let me check quickly if I have that somewhere. That will be, sorry, meter. That's no Newton. There is meter per second square. Yeah, so that's the acceleration actually. The gravity, okay. Okay. All right. And actually, one thing, if we come in that part, we stop. If we will not add the stripping between minus 2 pi to pi, so 360. That will be adding the angles actually. But as you saw, changing the orientation, it gives some error on Neo currently. So that should be included as well. So I will do rotation 180, 270, 360, and it will be adding. Okay, so we can spin and we will add. So that's why we don't need to know how